Welcome back. In our ongoing exploration of EMC principles, we now turn our attention to minimizing parasitic inductance in PCB design, a crucial step in reducing galvanic coupling effects. To prevent parasitic inductance, we need to avoid big loop areas and common impedance paths as we saw earlier. The two circuits shown emphasize this situation once again, where the common impedance should be avoided when designing the PCB. So how do we reduce parasitic inductance? This can be achieved by minimizing the loop size within the circuit, as illustrated by comparing the two sketches. The right sketch, depicting a smaller loop area, is optimal for EMC because it not only mitigates galvanic coupling, but also diminishes parasitic inductive coupling. Components in reality come with inherent parasitic inductances and capacitances, hence the term parasitic. These elements manifest due to the physical layout or connecting cables. For example, if we buy a resistor, there are parasitic inductances due to the connectors and parasitic capacitances between the connectors. Moving on to capacitive coupling, we find that it occurs when two conductors are in close proximity, like when two traces on a PCB running side by side. A variable electric field between them results in a displacement current, so the two traces act like a capacitor. To determine the capacitive coupling between two conductors, we can approximate the capacitance with the formula shown. The formula incorporates the permittivity of the dielectric material between the conductors. Permittivity, which describes how polarizable the dielectric material is, affects the storage of electric fields. Two materials, air and FR4, are particularly relevant due to their distinct permittivity values, which must be considered in PCB design. If we want to determine the capacitance of two PCB traces running on top of each other, we can use the formula of a simple plate capacitor as shown. To put theory into practice, consider a PCB with an operational amplifier. A signal line runs on the top plane, and the amplifier is designed on the bottom plane. Its feedback line runs exactly below the signal line. This leads to a parasitic capacitance, as shown. We can calculate the parasitic capacitance due to the given geometries of the two traces. Please have a look at the online documents for more details on the corresponding lab session.